Alright guys, so today we're going to talk about titrations and titration curves, and hopefully by the time we're done with these notes you'll understand what a titration is and kind of how they work, and be able to calculate the pH at different points during a titration, as well as interpret titration curves. So a titration is a laboratory method, so it's something we do in the lab to determine the concentration of a substance. It's also known as volumetric analysis. I left those letters there to remind me what to put in the blanks. Okay, it's also known as volumetric analysis because we're using the volumes of things to figure out concentration. Now when we do this, you have one substance that you know all about, that you know its concentration, and that is called the titrant. Okay, the one you are trying to figure out the concentration, that is the analyte. Okay. So when we do this, pretty much what we do is you have the analyte in a flask, and you know the starting volume of the analyte, although you don't know the concentration, and you add titrant a little bit at a time until you notice a drastic change in pH. Okay, using the volumes of the two solutions that were added together, you can figure out the concentration of the analyte. Okay, and the way that we measure this is we look at a titration curve. Now it's also known as a pH curve because the y-axis is going to be set up as the pH. The x-axis is usually the volume of the titrant. So how much of that solution of known concentration has been added throughout the experiment. Okay, so I have a couple of different examples of titration curves that you might see. Okay, looking at this one, if I look at this curve, this first one looks kind of weird because it almost looks like there's two equivalence points. And actually there are two equivalence points. First off, the pH is starting low. It's starting very low. And so I know that the analyte has to be a strong acid. And if I look at the first pH value, the equivalence point is going to be at 7. I know it's kind of hard to see this, but it's right at 7. And so since the equivalence point is right there at 7, I'm going to say that they're both a strong acid, strong base. Now, the reason this one has two equivalence points in it is that this is a diprotic acid. You actually have two protons that are being reacted. So this is the point at which the first one reacts, and this is the point at which the second one has fully reacted with the base. Okay, if I had to guess, looking at this pH curve, this is sulfuric acid, H2SO4, because sulfuric acid is a strong acid, and you're probably reacting it with a strong base like sodium hydroxide. That happens pretty frequently. And then the second proton is reacted right here, and so what's left is that sulfate ion. So this is the first hydrogen reacting, this is the second hydrogen reacting, and then you're completely out of hydrogens. Okay. Looking at this next curve, this is 7 right here. If I look at the equivalence point for this one, I notice that the equivalence point is not at 7. And if I look at this, I know we're starting at a pH under 7, so we're starting with an acid. Some type of acid is the analyte because the pH is starting under 7, but it's probably a weak acid because it's not starting very low. So this is probably a weak acid, and as we add the strong base, we do get to that equivalence point. But at that point, because we reacted a weak acid and a strong base, we get a basic salt, and so the pH at the equivalence point is basic. It's above 7. Okay. Looking at the next curve, since this one's starting above 7, so again, here's 7 on my curve. Looking at this one, it looks like we're starting with a base because we're starting with something above 7. It's not close to 14, so I'm going to say this is probably a weak base. And if we're adding this acid, I notice that the equivalence point seems to be below 7, so I'm going to say that we're adding a strong acid. So this is probably a weak base, strong acid titration. Okay. And then in this last one, the pH is starting very low, so I'm going to say this is probably a strong acid. And again, my equivalence point is pretty darn close to 7. So I'm going to say this is a strong acid, strong base reaction. Okay. So again, in this first one, the analyte, the thing you're starting with, is probably diprotic acid. And you're reacting it with a strong base. In the second graph, you are starting with a weak acid, a weak monoprotic acid, right? And reacting it with a strong base, which is why the pH at the equivalence point is kind of basic. Again, in this third one, we're starting with a weak base. And we're adding a strong acid, which is why the pH is acidic at that equivalence point. And then in this last titration curve, we have a strong acid and a strong base. And so you get that classic pH curve where you're starting low, there's a big jump. The middle of that jump is at pH 7, and then it ends high. Okay? All right. So again, let's look at this, this curve and look at the different parts of the curve, right? So in this one, again, we're starting with a base because the pH is above 7. So I know I'm starting with something basic. And at point A, all you have is the analyte. So at the beginning, the pH is completely dependent upon the analyte. In this case, whatever base it is, I would have to find the pH of the base at that point. Now, as soon as that first drop of acid, because we're adding acid in this case, as soon as that first drop of the titrant hits the analyte, what we have is a mixture of acid and base. And so as the acid and base are added, the pH has to be calculated using the Henderson-Hasselbalch equation. Okay, that's because this is known as the buffer region. What we have is a mixture of the acid and some salt, right? That is its conjugate. And so since we're in that buffer region, we have to use the buffer equation, the Henderson-Hasselbalch equation, to calculate the pH through those points. Now, B is known as the half equivalence point. Right? At this point, half of the analyte has reacted, and you've got half left. So in your solution, half of the molecules, the ones that aren't water anyway, half of the molecules are the analyte, and the other half is the conjugate. So what happens is the substance and its conjugate have a 1-to-1 ratio at this point. So at that point, pH is equal to pKa, although in this case it would be pKb, right? Well, no, actually, it would still be pKa because we're using the Henderson-Hasselbalch equation. So even if I had a Kb because I'm starting with a base, I would have to use Kw to switch that. So pH is equal to pKa because you're using the Henderson-Hasselbalch equation that only has Ka in it, right? And so if I negative log my Ka value, I get that pH. C is the equivalence point. Okay, at that point, the analyte has been completely reacted. Right? It's formed products. And the pH at that point depends on the salt that forms. So at that point, this is now a hydrolysis problem. You have to look at the salt that is formed in the reaction, look at the equation for the reaction, look at the salt that forms, determine whether it's acidic or basic, right? Take out the spectator ion, write the reaction for the hydrolysis of that salt, and then calculate the pH from there. Okay, now after that point, after the equivalence point, the pH depends on the excess titrant added to the solution. So in this case, we were adding an acid. Whatever number of acid molecules is divided by the total volume we've got, that'll give me the concentration, and then I can negative log that and get pH. Okay, so after the equivalence point, we're just looking at it as either a strong acid or a strong base solution, and calculating the pH from there. Okay, all right. So again, looking at this titration curve, okay, you have an acid here because we're starting with something a pH less than 7. You have your equivalence point. You have the titration endpoint. So that's kind of where the indicator changes colors. It's kind of the top of that vertical. And the deal is there's not much difference between the equivalence point and that titration endpoint. The volume is completely negligible. So actually, when you guys did the titration in Chem 1 between hydrochloric acid and sodium hydroxide, we used phenolphthalein, which changes colors at around pH 8, not 7. And so that pH of 8 was actually the end point where it changed color. We had gone beyond the equivalence point just a little bit, but it was so little that it didn't really matter when we were calculating, when we were using those volumes in our calculation of concentration. So what you really want to do is use an indicator that is going to change color to signal neutralization. And phenolphthalein is not the only one by any means. There are several different acid-base indicators that are out there. Only strong acid, strong base titrations have a pH of 7 at the equivalence point. Okay, different indicators have to be used for different titrations. So if I'm doing something with a weak acid and a strong base, and I know that the equivalence point is going to be above 7, I need the endpoint. The endpoint's going to be a little bit higher as well, and so I need something that has kind of a higher, that's going to change colors at a higher pH. Okay. What you need to do is choose an indicator with a pKa value close to the pH at the endpoint, or even the equivalence point, but we'll say endpoint. Okay, so somewhere in here where you want it to change color, look at the Ka values for each of those indicators, negative log it, right? That's what the little p means. That means you negative log it. So look at the Ka value for the different indicators, negative log them, and look at the values you get. You want the one that's going to change colors right about the time your solution should be reaching its endpoint, okay? So that's what I need you guys to understand. And tomorrow in class, what we're going to do is we're going to start doing the calculations, okay? And really what's going to be very important, besides knowing how to interpret a titration curve, is understanding that at different points in the curve, you're going to have to use different equations. Okay, you're going to have to take a different approach depending on where you are in the titration. And so this is kind of the thing that ends up being tricky for students, but I'm really hoping that by looking at these and understanding the different parts of a titration curve, that you'll be able to approach these problems with some ease.